Hey students, we've gotten to that point in Math 143 where we now know all the tests, so you won't learn any more tests for working with infinite series. And now it's time to put it all together. So we're on section 11.7 today, and the title of that is Strategy for Testing Series. So what I want to do is just kind of a practice. And that's what your homework will be, is practicing using all the tests. It's not going to tell you which test to use now. You are going to have to see or figure out, based on the series that you're given, which test works, and then decide whether it's convergent or divergent, or in some cases, absolutely convergent, conditionally convergent, or divergent. So let's just do a quick rundown on the tests that we have so far. We started off, of course, there's the test for divergence. Test for divergence is the test that you should be doing in your head every time you see a series. You should be thinking, can I apply the test for divergence? It's kind of the first thing you should think. Right? So write that down. You should be taking notes right now, and this is going to be kind of the order that you want to think. Test for divergence is the first test to be using, but you should kind of just be able to eyeball it. Does the test for divergence apply? Does it give me any information or not? Next, we've got the geometric series test. We have telescoping series. Telescoping is kind of obscure, but it does show up, right? And here's one thing to notice. There are exactly two situations at this point where we can calculate the exact value of a series. It's either got to be geometric or telescoping. So if you get instructions that say find the sum of the series, or it'll be something like this: determine whether it's convergent or divergent, and if convergent, find the sum. It will have to either be geometric or telescoping. And it's pretty easy to recognize whether it's geometric. So if it's not geometric and the instructions say find the sum, then you're guaranteed that it's got to be telescoping. Right? So then there's telescoping. What else did we get? So the next test we got the integral test. P-series. All right, so the p-test. We've got the comparison test and the limit comparison test. We've got alternating series test. Oh, I guess let me go in order here. We've got the ratio and root tests. And then the last one here, we put it right down here, alternating series test. All right, so there's your tests. And I'm going to leave this up for a minute. And what I want to do is I'm just going to do a few examples. And your homework is going to ask you to do a bunch of series. And what I want to do is kind of just look at it and talk about how we should think about this. Think about these. So the first one I want to look at is sum n equals 1 to infinity. Minus 1 to the n, n squared minus 1 over n, is it n cubed? Yeah, n cubed plus 1. All right, when we look at this one, you should say, that's an alternating series. And you should also be able to see from this that this is going to converge by the alternating series test. All right, that tells you it's alternating. When you look at this, the ratio, we've got polynomial over polynomial. Top has smaller degree than the bottom. That limit is going to be 0. So this one should very quickly, you should be able to say, since limit as n goes to infinity of n squared minus 1 over n cubed plus 1 equals 0, the series converges by alternating series test. Now, I wasn't specific about the instructions here. I mean, the problems in your book, the instructions actually say just determine whether it converges or diverges. But we know about conditional versus absolute convergence, and so let's take this a little bit further and ask the question, is it conditionally convergent or absolutely convergent? So absolute convergence would require us to put absolute value bars around that, which would give us this series right here. right? We just get rid of that minus 1 at the end. And now, what do you think? When you look at this one, you should say, this is going to behave like a 1 over n, right? It's an n squared over n cubed when you look at the dominating terms. And that's what you should be doing when you see polynomial over polynomial. Look at the ratio of the leading terms, right? The dominating terms really determine how the series is going to behave. And so you should suspect in your head this one is going to diverge. And typically when you have polynomial over polynomial, you're either going to use comparison or limit comparison test. I'm just going to go with limit comparison, and we're going to limit compare it with 1 over n. So we can say since limit as n goes to infinity of n squared minus 1 over n cubed plus 1 over 1 over n, that's equal to limit as n goes to infinity of n cubed minus n over n cubed plus 1. I just flipped and multiplied here. And that limit is equal to 1. And sum n equals 1 to infinity of 1 over n diverges. Why? Because that's a p series where p equals 1. So does sum n equals 1 to infinity n squared minus 1 over n cubed plus 1 by the limit comparison test. Okay, so what does that tell us then? It tells us that the original series with absolute value bars around it diverges, which means that this is not absolutely convergent, it's only conditionally convergent. So our conclusion then, sum n equals 1 to infinity minus 1 to the n squared minus 1 over n cubed plus 1 is conditionally convergent. And so think about what tests we used. We used the alternating series test because it was clearly alternating. And then we used the limit comparison test because what did we have here? We had something that was going to behave like a p series that we knew about, right? When it behaves like something we know, that's going to be comparison or limit comparison, right? So I want you to be thinking about how do you decide which test to use, right? And right, because when you get to an exam, you don't want to be using the wrong test, right, and wasting time. You want to go to the correct test right off the bat. Okay, next example. This one here is going to be sum n equals 1 to infinity minus 1 to the n, n to the 4th over 4 to the n. This one's definitely alternating. And because, right, so it's definitely alternating. And if you notice, we got polynomial on the top, exponential in the bottom. Exponential always beats polynomial. So by the alternating series test, this one is going to converge. So alternating series test would allow us to show it converges. But also, when you see something of this form, polynomial in the top, exponential in the bottom, right? That's also a place where the ratio test could help. And so in fact, I'm going to show that this series is absolutely convergent. I'm going to jump straight to absolute convergence by applying the ratio test. So let's see what happens here. Since limit as n goes to infinity. And I should point out, sometimes there's more than one correct test. Sometimes you can, or sometimes you can shortcut a process. If you already suspect that it's absolutely convergent by either the ratio or root test, go straight for it. You don't have to waste time showing first that the original series converges and then the series, when it has absolute values around it, also converges. You can go straight to showing it's absolutely convergent. So since limit minus 1 to the n plus 1, n plus 1 to the 4th over 4 to the n plus 1, divided by minus 1 to the n to the 4th over 4 to the n. all in absolute values. Equals, so now I'm going to flip, I'm going to multiply, I'm going to get rid of the minus ones and the absolute values. So all in one step, we're going to have limit as n goes to infinity, n plus 1 to the fourth over 4 to the n plus 1 times 4 to the n over n to the fourth. We can cancel some 4's here, so this will be a limit as n goes to infinity. N plus 1 over n to the fourth times 1/4, which is equal to, this part right here is approaching 1, and so we get 1/4, which is less than 1. The series is absolutely convergent by the ratio test. So here's some advice, I guess, is first of all, when you see something and you suspect that it's absolutely convergent, or let's say it this way, when you suspect that the ratio test applies, and definitely if you have polynomial over exponential, the ratio test is going to do the job. Polynomial over polynomial, the ratio test never works. It gives you a limit of 1. But if you have polynomial and exponential, ratio test is a good choice, and that allows you to shortcut the process. You can jump straight to showing that it's absolutely convergent. Next one. Sum n equals 1 to infinity n times sine of 1 over n. Now, sometimes it's kind of clear what test to use, right? When the ratio test, the root test, comparison or limit comparison, p-series, those ones are fairly obvious. Integral test is sort of the one that I'm not going to try. So here's the order that I usually think of. In my head, I'm going to check test for divergence real quick. I'm going to decide, is it geometric or telescoping, especially geometric. This one's clearly not geometric. I don't really want to integrate this. So integral test is going to be sort of my last choice. It's not a p-series. I don't see how to do a comparison, although it may be a limit comparison. Ratio and root, no, and it's not an alternating series. So by process of elimination, I don't have a whole lot. I've got test for divergence first, and then limit comparison test. Those are really my only two options in this case. So let's just try test for divergence. Limit as n goes to infinity, n sine 1 over n. Now that is an infinity times 0. So I can rewrite this as limit as n goes to infinity of sine 1 over n divided by 1 over n. Now this is 0 over 0, which means I can apply L'Hopital's rule. And we'll get a negative 1 over n squared cosine 1 over n divided by negative 1 over n squared. Cancel the negative 1 over n squareds, and what we get is a limit of 1, which is not equal to 0. And so what does that tell us? It tells us that the series diverges by test for divergence. So the series diverges by test for divergence. So oftentimes in deciding what test to use, it's a process of elimination, right? I just said, okay, I don't recognize it as a number of these tests are not going to apply. So what I was left with is maybe limit comparison test, and I had not done test for divergence yet. And so that was one that I couldn't really do in my head. I actually had to crank it out. But when you get a limit that's not equal to 0, right, then by test for divergence, it converges. It diverges. We can do a couple more examples. Okay, so the next one, and by the way, each one of these is from your book. I'm not taking them from anywhere special. This is -1 to the n divided by what's called the cosh of n. Now, cosh is this is a hyperbolic cosine. This is something that we used to cover fairly regularly in calculus, but even I've started to neglect this. All it is a definition. The cosh, right, the hyperbolic cosine, is defined this way: e to the n plus e to the minus n divided by 2. That's it. So the first step is to rewrite this. This will be -1 to the n times 2 over e to the n plus e to the minus n. Okay, so yeah, this one's alternating. So you could use the alternating series test, right? If you just look at the sequence inside here, right, that limit is going to go to 0. So this series converges by the alternating series test. So one thing you could do, converge by alternating series test. If the question asks whether it's absolutely convergent or not, well, okay, so if I put the absolute value bars around, now I'm considering sum n equals 1 to infinity of 2 over e to the n plus e to the minus n. And now, what do you think? Well, this one's kind of like, it's almost geometric, right? The e to the n there. So I'm kind of thinking, could I compare this to a geometric series? And the answer is yes, right? So we can say since 2 over e to the n plus e to the minus n is less than or equal to 2 over e to the n, and sum n equals 1 to infinity of 2 over e to the n. Let me rewrite this so it makes it look more clearly geometric. It's a 1 over e raised to the n with a 2 out front. All right, this converges by the geometric series test. So does the original series here by the comparison test, right? I showed that our series is smaller than one that converges. Than one that converges. And so now, what did we just show? We showed that this series right here is absolutely convergent. So therefore, the original series sum n equals 1 to infinity minus 1 to the n over cosh of n is absolutely convergent. And I've got one more picked out that I wanted to look at. Oh, and you should say, no, how did you know? Let's see, the series I was looking at was this one, right, with the absolute values. How did I know to use comparison test? Well, I looked at this and I said, oh, adding in the denominator makes the fraction smaller. So the fraction is smaller than 2 over e to the n. Oh, e to the n, that feels very geometric. Right, so it sort of led me straight to geometric series. Okay, so one more example. Sum n equals 1 to infinity. N factorial raised to the n? Is that an n? Yep, the n. Divided by n raised to the 4n. All right, now I said, I said if you see a factorial, it's almost always going to be ratio test. But notice here, we've got a factorial raised to the nth power. So I think life will be easier if we use the root test, right? The root will get rid of these nth powers. So I'm going to go to the root test. So if I take the limit as n goes to infinity of the nth root of the absolute value, I don't really need absolute value bars here because I've got everything positive, but I'll put it in just for fun. N factorial to the n over n to the 4n. That's equal to the limit as n goes to infinity. So now let's take the nth root. What we'll get is n factorial in the top and n to the 4th in the denominator. Factorial definitely beats n to the 4th. That limit is equal to infinity, which is clearly bigger than 1. The series diverges by the root test. Okay, so I wanted to do this one because I know I said factorial almost always means you should try using the ratio test. Here's a situation where it's kind of a mixture, right? We've got nth powers, and then we also have a factorial. Because of those nth powers, I wanted to get rid of them by using the root test. And so here's one situation where we use the root test even though we see factorials. Still, the rule of thumb stands, and we certainly could have used the ratio test here. We would have gotten the same answer. Okay, so you've got a bunch of homeworks to work on, and this is the time to put it all together. Remember, right, first of all, learning how to decide whether a series converges or diverges, that is just, it takes practice, right? The more you practice, the better you'll get at it. Also, you should know the statement and how to use each one of these tests. And so oftentimes it becomes sort of you recognize there's certain ones that fit into certain categories. If they don't fit into certain categories, it's a process of elimination, right? And you might have one or two tests that are left, and those are the ones that you have to try. Okay, so we will see you next time. All right, bye-bye.